In this example, we will illustrate how knowledge-based prediction of toxicity can be used within a multi-parameter optimization environment to guide the selection and design of compounds with a good balance of properties and reduced risk of toxicity. We will explore a library of compounds with experimental inhibition data against the cyclooxygenase 2 target with the goal of identifying a high-quality lead series comparable with the best-in-class celecoxib. However, we should consider that other COX-2 inhibitors, including rofecoxib and valdecoxib, were withdrawn from the market due to adverse events. We begin by selecting the File Open menu and choosing the file COX-2 library. This is a dataset containing 152 compounds with potency data measured as pKis against the COX-2 target. This represents a small library of compounds which have been screened for potency and from which we would like to identify a high-quality lead series. To explore the chemical diversity of this library and the distribution of potency across it, we are going to first take a look at a chemical space plot of this data. Click on the Visualization tab on the left. Click on the Chemical Space button and then Create. In the dialog box that appears, type in a name for the chemical space plot you're about to create. In this example, we've called it COX-2 space. We can build different types of chemical space plots based on chemical structure or property data, and choose whether to generate a 2D or 3D space. But in this case, we're going to use the defaults: a chemical structure, the visual clustering method, and a 2D space. Click the OK button and wait until the chemical space has been created and the dialog box disappears. When the process is complete, a chemical space will be displayed. In the Visualization tab, click the Detach button to create a separate window containing this chemical space. This will enable us to keep the chemical space plot visible as we explore the library. First, we will colour the points by the experimental potency to identify the most potent chemistries. In the detached plot, click on the colour block in the key and, in the Format by Property window, select pKi from the Source menu and then click OK. In the resulting plot, we can see the clusters containing the most potent compounds. By default, these are coloured yellow. However, the most potent compounds are not necessarily the best starting point for a high-quality lead series. Ideally, we would like to identify a potent series that is also likely to have an appropriate balance of absorption, distribution, metabolism, and elimination properties. StarDrop's probabilistic scoring approach to MPO makes it easy to identify the chemistries that are most likely to achieve the required profile. Change to the Scoring tab in StarDrop and click on the Open button to load a new scoring profile. In the Load Profile window, select the COX-2 scoring profile.apd file and click Open. The scoring profile will be displayed in the Scoring tab. Click on the arrow button to calculate the score for each compound based on the experimental potency and predicted ADME properties. The models required to predict the ADME properties in the profile will be run automatically and the results will appear as columns in the dataset. Right-click on the header of the COX-2 scoring profile column and select the Sort Descending menu option. The highest scoring compounds will come to the top of the dataset. We can now colour the points in the chemical space by the overall score. To do this, click on the colour block in the key of the detached plot, select COX-2 scoring profile from the Source menu in the Format by Property window, and then click OK. From this, we can see that the most potent cluster is now quite red, indicating that it is unlikely to have acceptable ADME properties. Alternative regions are highlighted in yellow and are more likely to have both good potency and good ADME properties. Note that celecoxib is one of the top scoring compounds, giving us confidence that the scoring profile is prioritizing high quality compounds for COX-2 inhibitors. If we select row 7 containing celecoxib, it will be highlighted in the chemical space. Note that 2 other regions are indicated as potential regions of high quality chemistry. So far, we have not considered the potential for toxicity, and for this we will use the Derek Nexus module for StarDrop. Change to the Models tab. At the bottom, you'll see the Derek Nexus branch, which you can expand by clicking on the arrow adjacent to the name to see a full list of toxicity predictors provided by the Derek Nexus module. Select the carcinogenicity, genotoxicity, hepatotoxicity, and mutagenicity endpoints by checking the adjacent boxes. Note that hepatotoxicity is in the organ toxicity branch under Derek Nexus. Click the arrow to run these predictions. This will take a few minutes. For this movie, we're going to skip to the results. Scrolling the dataset to the right enables you to see the predictions for the individual endpoints in additional columns. These correspond to structural alerts with levels of likelihood based upon precedents from experimental data. A no report outcome for an endpoint indicates that the query compound does not contain any structural alerts associated with that endpoint, and there are no reasons based upon the physical properties of the compound to predict either activity or inactivity. In the case of mutagenicity, Derek Nexus may also predict inactive, which indicates that the properties of the compound suggest it is likely not to be mutagenic. Other possible results in ascending order of likelihood are equivocal, plausible, and probable, and the alerts in the dataset are highlighted in orange. From these results we can see that there is an indication of the potential for toxicity for some of the top scoring compounds. We can visualize the results in the library's chemical space. In the chemical space plot window, click on the color block in the key as we did previously and select hepatotoxicity from the source menu in the Format by Property window. In the resulting chemical space, we can see that some regions of the chemical space are highlighted as having an equivocal or plausible likelihood of hepatotoxicity, including one of the high scoring regions. We can include the toxicity predictions in a scoring profile to prioritize potent compounds with a good balance of ADME properties and a reduced risk of toxicity. Change to the Scoring tab and click on the Load button again to load a new scoring profile. In the Load Profile window, select the file COX2 scoring profile with toxicity.apd and click Open. The scoring profile will be displayed in the Scoring tab, as before. Click on the arrow button to calculate the score for each compound based upon the experimental potency, predicted ADME properties and toxicities. By colouring the points in the chemical space using the new score calculated with the toxicity endpoints in the same way as we did before, we can now see that there is one region in the chemical space which appears to contain the majority of the top scoring compounds. This indicates that this chemistry has the highest chance of providing a high quality series. You can find the corresponding points in the dataset by using the mouse to draw around the points in the chemical space. Based on these results, an appropriate strategy would be to focus experimental and synthetic resources on the highest scoring compounds. However, given the potency and good properties of some alternative areas of chemistry, these should not be rejected outright. As reflected by their scores, predictions of toxicity and other properties are not definitive, and therefore it would be appropriate to sample a small number of additional compounds for further tests, to confirm the predicted hypothesis and avoid missing valuable opportunities due to uncertain data. So far, we have been considering strategies for selecting compounds, taking into account the risk of toxicity. Now we will illustrate how we can explore strategies to redesign compounds to reduce this risk. Draw around the small cluster of compounds, holding down the left mouse button to select the corresponding compounds in the dataset. Note that one of the selected compounds is lumiracoxib. This compound has been withdrawn from the market in several countries, mostly due to hepatotoxicity concerns, and has never been approved for use in the US. We can use the interactive designer and the glowing molecule to identify substructures causing alerts in order to guide efforts to redesign compounds with reduced risk of toxicity. Change to the Design tab and select the row containing lumiracoxib. Its structure will be copied into the editor. In the list of predicted properties below the editor, select hepatotoxicity to highlight the structural alert for this endpoint. Use the editor to modify the structure of the carboxymethyl. For example, use the Eraser tool to delete the methylene, and then the Bonds tool to join the carboxyl group directly to the phenyl. As we edit the structure, the predicted properties in the table will update, enabling the properties to be monitored simultaneously. The new compound doesn't have a predicted risk of hepatotoxicity, suggesting that it may be of interest for further exploration. This example has used some of StarDrop's capabilities to illustrate how knowledge-based prediction of toxicity, provided by the Derek Nexus module for StarDrop, can be used in early drug discovery to reduce the risk of encountering toxicity issues downstream. For more examples, exploring some of StarDrop's other features for compound design and optimization, take a look at the tutorial section in the Optibrium community.